Welcome back to this series on graph theory. Today we're going to wrap up our look at paths and cycles. I'll start out today by introducing the Petersen graph. The Petersen graph is the graph whose vertices are two-element subsets of a five-element set and whose edges are pairs of disjoint subsets. Thus, to construct the Petersen graph, we need to write down some five-element set. For example, we can use the set of integers from 1 to 5. Then for each two-element subset of this five-element set, we add a vertex to our graph. For example, we have the two-element subset containing the elements 1 and 2. We have the subset containing elements 3 and 4. We have one containing 5 and 1, 2 and 3, 4 and 5. Now there are 5 subsets remaining. One contains 3 and 5, 1 and 3, 4 and 1, 2 and 4, and finally 5 and 2. Now these are in fact all the possible two-element subsets because we can form 5 choose 2 such subsets, and 5 choose 2 is 5 factorial divided by 2 factorial times 3 factorial, which is equal to 5 times 4 divided by 2, which is 10. Thus indeed we found 10 distinct two-element subsets, and so this is all of them. We now need to add the edges to our Petersen graph, and by the definition of the Petersen graph, there's an edge between two vertices if the corresponding subsets are disjoint. For example, we have an edge between the subsets containing 1 and 2 and the subset containing 4 and 5. Similarly, we have an edge between the subset containing 1 and 2 and the subset containing 3 and 5. For example, we don't have an edge between the subset containing 1 and 2 and the subset containing 5 and 2 because those two subsets are not disjoint, so there would not be an edge here. I'll now draw the remaining edges. This gives us one way of drawing the Petersen graph, and perhaps this is the easiest one to remember. So if we just draw it again from scratch, in the interior we have this star shape, and then in the exterior we have a 5-cycle that connects to each of the rays of the star shape. There are also two other nice ways of drawing the Petersen graph, which I'll show. The first one has a 6-cycle on the exterior, and then in the interior we have 4 remaining vertices, And these are connected in the following way. We can also draw the Petersen graph with a 9 cycle on the outside. Then we have one vertex remaining in the middle. And finally, we need to draw some chords in the 9 cycle. And this completes the third drawing of the Petersen graph. Now, when we want to prove things about the Petersen graph, it's useful to not look at the drawing, but rather focus on the way it's defined in terms of two-element subsets. In what follows, we'll prove that the Petersen graph has a girth of 5. We'll formulate this as a proposition. The Petersen graph has girth 5. We'll prove this in the following way. First, we observe that the Petersen graph contains a 5 cycle. In the first drawing that we made, this 5 cycle could be the exterior cycle of the drawing. For ease of notation, we'll call the Petersen graph G. Since G has a 5 cycle, we conclude that the girth of G has to be less than or equal than 5, because the girth is the length of the shortest cycle, and we found a cycle of length 5, thus the shortest cycle needs to be less than or equal to 5. We finished the proof by showing that the Petersen graph can't contain a 3 cycle or a 4 cycle. Suppose first that the Petersen graph contains a 3 cycle. We know by definition that the vertices of the Petersen graph are two-element subsets. And we also know that because all of these two-element subsets share edges with each other, they have to be pairwise disjoint. From this, it now follows that all of these elements in the two-element subset have to be distinct. But there are 6 of these elements, and we're only taking subsets of a 5-element set. So this is a contradiction, and in fact, we can't have such a 3 cycle. Next, we show that it's also impossible to have a 4 cycle in the Petersen graph. Assume again, for the sake of contradiction, that we would have such a 4 cycle. Again, the vertices are two-element subsets. And we know that because we don't have an edge between these two corners of this square, that they have to share an element. If they would be disjoint, then by the definition of the Petersen graph, they would have an edge between them. Now, if we focus on one of the other corners, we know that this has to be a two-element subset that is disjoint from both of its neighbors. So it has to be disjoint from AB and from BC. So we need to have some other elements, DE, in that subset. However, now we've again used all the 5 elements from our 5-element set. So there aren't any remaining elements that we could assign to this other corner of the square So in fact, such a square can't exist in the Petersen graph. In other words, any two non-adjacent vertices in the Petersen graph can have at most one neighbor, and having a square in the Petersen graph would require two non-adjacent vertices to have two neighbors. Thus, we've also shown that the Petersen graph can't contain any 4-cycle. Hence, from the fact that G can't contain a 3 or a 4-cycle, it follows that the girth of G has to be greater or equal than 5. And now we have both inequalities, and from this it now follows that the girth of G is 5, as we wanted to prove. So far, we've defined several parameters for paths and cycles, respectively. We defined the diameter of a graph to be the largest distance between any two of its vertices. And we've defined the circumference of a graph as the largest cycle it contains. Finally, we defined the girth of a graph as the length of the smallest cycle it contains. So on the top row, we have the minimal objects, and on the bottom row, we have the corresponding maximal objects. This table suggests that we should find some minimal object to describe the length of paths in a graph G. Now, first guess might be to let this parameter be the length of a shortest path in our graph. However, as soon as our graph has a single vertex, say V, there is a trivial path that just goes from V to V that has length 0, and this is always there in any graph that has at least one vertex. So in this case, using the length of the shortest path as a parameter wouldn't make any sense, because as soon as G has a vertex, the value of that parameter would be 0. Instead, what one does is one looks at the minimum over all the maximal distances one can achieve from a given vertex. To illustrate this, I'll draw an example graph G. Now, if we select any vertex V in G, then we can calculate its distances to all other vertices in the graph. For example, if we call these vertices A, B, and C, then the distance from V to A is equal to the distance from V to B and from V to C, and this distance is just 1. If instead of V we select B as our starting vertex, then we can again calculate the distance from B to any other vertex in the graph. We have the distance between B and V is equal to 1. However, the distance between B and A and between B and C is equal to 2. Finally, selecting any other vertex, either A or C, will give the same result as for B, since the situation is symmetric. Now, for any initial choice of vertex, so for example, if we choose V first, we can look at the maximal distance that it has to any other vertex. So in this case, the maximum over all other vertices, call them X in the vertex set of G, between our first selection, so that's V, and the second vertex X, in this case is equal to 1. To be absolutely clear, what we're doing here is we're fixing the first vertex, V, and then we're looking at its distances to all other vertices in the graph G. And then we select the distance that is the largest as the value for this maximum. Similarly, we can look at the maximal distance for a fixed vertex B to any other vertex in the graph. And in this case, because B has distance 2 from both A and C, this maximum is 2. As we've mentioned before, this is the same as if we choose first A and then look at its distance to any other vertex in the graph, and also if we first choose C. Now that we've calculated the maximal distances between any starting vertex in G and all other vertices in the graph, we can now look what the lowest value is over all these maxima. If we now minimize over all these maximal values, what we get is the minimum over vertices x and g of the maximum over vertices y in G of the distance between x and y. In our concrete case, the minima over all these maximal values that we've calculated happens to be 1, and this is attained by the vertex v. The quantity that I've written in blue is called the radius of a graph, and this is the minimal object that we'll be using for distances in a graph. Moreover, any vertex for which the expression on the left attains the value of the radius is called central. Intuitively, what the radius is trying to do is it's trying to minimize the largest distance from one given vertex to any other vertex. And the vertex which is close to the middle of a graph will generally achieve this best. Let's write down the definition of radius for clarity. The radius of a graph G which we write rad G is the quantity. So we take the minimum over all vertices x in G of the maximum over all vertices y in G of the distance between x and y. Schematically, if we have our graph G given as a blob, then the diameter of G measures the longest distance between any two vertices in G, while the radius tells us how small we can make the maximal distance from any other vertex to some vertex. This geometric intuition would suggest that the diameter of G would be twice the radius. This is in fact too strong, but if we turn this equality into an inequality, then it becomes a true proposition, which we'll prove next. We have that the radius of a graph G is less than or equal to the diameter of G, which is less than or equal to 2 times the radius of G. In the proof, we need to distinguish two cases. In the first case, G contains two vertices, not connected by a path. If we call these vertices u and v respectively, then the distance between u and v is infinite by definition, and therefore the diameter of G, which is the maximum over all vertices u and v in the vertex set of G of their respective distances, this will also be infinite. Finally, the radius of G, which is the minimum over vertices x in the vertex set of G of the maximum of vertices y in the vertex set of G of the distance between x and y. This will also be infinite. To see this, let W be any vertex in our graph G, and we have these vertices u and v which don't contain a path between them. If there were some path p between W and v, and there would be some other path q between W, and U, then we could find a path between U and V as follows. We would traverse Q until the first intersection it has with P, and then we would go along P to V. If Q and P don't intersect, then we would proceed along U to W and then go from W to V along P. Because there is no path between U and V, this shows that for any vertex W in our graph, it can have at most one path between it and either U or V. In other words, there is no path between W and either U or V. This implies that the maximum over all y in the vertex set of G of the distance between W and y is infinite, because there is a vertex which we can't reach from W. And this holds for all vertices W in G, which means that the minimum over these maximal quantities is also infinite. Therefore, in this case, the diameter is infinite and the radius is infinite. Therefore, the inequality that we're looking for, so the radius less than equal the diameter is less than equal 2 times the radius, these quantities are all infinite, and therefore, in this case, the inequalities hold. Thus, we've dealt with the first case, and we can now turn to the second case, where any two vertices of G are connected by some path. We now let P be a path that attains the diameter of G. Thus P joins two vertices, U and V. And these are the two vertices that have the largest distance in G. And P is the shortest path between these vertices. We now consider the radius of this path P, which we know is by definition the minimum over all vertices X in the path of the maximum of all vertices Y in the path of the distance between X and Y. We now let X be a central vertex of P. Recall that this means that X attains the value of the radius of P. In other words, X minimizes its maximal distances from all other vertices in the path. Now, it's relatively apparent that X, in order to be a central vertex, it has to be at the approximate midpoint of the path P. First, suppose that the number of vertices in our path is odd. Then there is some vertex in P whose distance from both of the endpoints is equal. So we have some vertex X, and the distance between X and U is equal to the distance between X and V. If we now let W be any other vertex in this path, then if W lies to the left of X, then its distance to V will be the maximal distance it has to any other vertex in the path. But since W is not yet at the midpoint of this path, we can move W over by one vertex and make this maximal distance between it and any other vertex in the path smaller. This shows that W can't be a central vertex. The exact same argument holds for vertices on the right-hand side of X, and these can also not be central vertices, so the only option that remains is that X is at this midpoint if it is a central vertex. If, on the other hand, the number of vertices in the path is even, then there isn't a vertex that is exactly in the center of the path. Instead, we have an edge that is in the middle of the path. And I now claim that any vertex on this edge is a central vertex. So in fact, such a path would have two central vertices. Now, on the left-hand side of this orange line, there's an equal number of vertices as there is on the right-hand side of the orange line. Suppose now that we choose some vertex w that lies to the left of x. Then again, the distance between w and v is the largest distance between w and any other vertex of the path. Then we can move w over to the right, and we decrease this maximal distance while not introducing another maximal distance. Therefore, if w lies to the left of x, then w is not a central vertex. Similarly, if we choose some w prime that lies to the right-hand side of y, which is the other vertex on this central edge, then we have that the distance between w prime and u is the maximal distance of w prime with any other vertex in the path, and we can reduce this maximal distance by moving w prime over to the left, while not increasing the distance between w prime and any other vertex beyond this new maximum. Therefore, again, if we have some vertex that lies to the right of y, then this vertex can't be central. It thus follows that x and y are the only two central vertices in the path. To sum up this discussion, we assume without loss of generality that the distance between the central vertex x and u is greater or equal than the distance between x and v. We now have that the distance between x and u is greater or equal than the diameter of g, so that's the length of our path p, divided by 2. In the case where p has an odd number of vertices, we would have an equality. And in the case where p has an even number of vertices, the distance between x and u would be the diameter of g plus 1 divided by 2. Therefore, 2 times the radius of p, which is equal to 2 times the distance between x and u, because x is a central vertex, and we've assumed that the distance between x and u is larger than the distance between x and v, we have that this quantity is greater or equal than the diameter of g. If we read this outer inequality, we almost have what we wanted to show. So we've shown that 2 times the radius of p is larger or equal than the diameter of g, but in fact what we want to show is that 2 times the radius of g is larger or equal than the diameter of g. It now remains to show that the radius of p is equal to the radius of g. First, note that the radius of p is always larger or equal than the radius of g because p is a subgraph of g. In the radius, we're taking a minimum over a set of vertices, and now because the set of vertices of p is a subset of the vertices of g, the minimum over the vertices of g will always be smaller or equal than the minimum over the vertices of p. Hence, we only need to show that the radius of p is less than or equal to the radius of g. And we do this by contradiction. Suppose that the radius of p is strictly larger than the radius of g. The radius of g is a minimum over all x in the vertex set of g, over the maximum over all y in the vertex set of g, of the distance between x and y. Now, because this minimum is strictly smaller than the radius of p, this means that there exists some w that is not in the path p that satisfies that the maximum over all vertices y in G of the distance between W and Y is strictly less than the radius of P, and we know that the radius of P by hypothesis is the distance between X and U. So we draw in W in our picture. Now, because we're in the second case where any two vertices of G are connected by a path, there's some path P that goes from W to V, and another path Q that goes from U to W. Moreover, we can assume that Q and P are the shortest paths between W and V or U respectively. Now, because the maximum over all distances between W and any other vertex is strictly smaller than the distance between X and U, we know in particular that the distance between W and U is strictly less than the distance between X and U, and also that the distance between W and V is strictly less than the distance between X and U. This now implies that the distance between W and U plus the distance between W and V is less than or equal to 2 times the distance between X and U minus 2. That's just a consequence of using both the strict inequalities we had before. Further, because X is at the approximate midpoint of the path P, we have that 2 times the distance between X and U is less than or equal to the diameter of G, which is the length of P, plus 1. In the case where P has an odd number of vertices and X is in the real middle of P, we have that 2 times the distance between X and U equals the diameter of G. And in the case where P has an even number of vertices, if we take twice the distance between X and U, we count one edge twice, and so we have that 2 times the distance between X and U is equal to the diameter of G plus 1. Using this inequality in what we were working on before, we can see that 2 times the distance between X and U minus 2 is less than or equal to the diameter of G minus 1, and this is strictly less than the diameter of G. This strict inequality that we've obtained now gives us a contradiction. I just noticed that I've called 2 different paths P, which is bad, so let's rename this blue path to R. The reason this strict inequality we've obtained is a contradiction is that we've now found a path between U and V that is strictly shorter than the shortest path P. How do we construct this path? Well, we start at U, and then we proceed along Q until the first point that it intersects the path R. From that point of intersection onwards, we then take R to V. Now, because the length of Q and R summed together is strictly less than the length of P, the path we obtain in this way from Q and R is also strictly shorter than the length of P. However, P was chosen to attain the diameter of G, and this means that P is a path that realizes the distance between U and V, and such a path is the shortest path, but we've now found some path that is strictly shorter than the shortest path, and this is a contradiction. Because assuming that the radius of P is strictly larger than the radius of G leads to a contradiction, we conclude that in fact the radius of P is less than or equal to the radius of G, which is exactly the remaining inequality we needed to show that those 2 quantities are in fact equal. So we've now shown that the diameter of G is less than or equal to 2 times the radius of G. Finally, we also need to show the first inequality, which is that the radius of G is less than or equal to the diameter of G. However, this follows directly from the definitions of the quantities in question, so we know that the radius of G is the minimum over all vertices X in the vertex set of G of the maximum over all vertices Y in the vertex set of G of the distance between X and Y. Now we know that the diameter of G is the maximum over all pairs of vertices in the vertex set of G, where we're maximizing the distance between x and y. And another way of writing this is taking the maximum twice. So we take the maximum first over all x in the vertex set of G, then take the maximum a second time over all y in the vertex set of G over the distance between x and y. And we now see that this expression also occurs in the definition of the radius of G. However, in the case of the diameter, we're taking a maximum over this expression, while in the case of the radius, we're taking a minimum over this expression, which means that the former is larger or equal than the latter. And this is exactly what we wanted to show. And this concludes the proof of this proposition. That's all for today's video. Next time we'll be looking at connectivity in graphs.